So our second presentation is from the Delta program of Holland.
Nederland krijgt te maken met klimaatverandering. Dat staat vast. Als we niks doen, dan lopen we de kans dat grote delen van Nederland aan overstromingsgevaar worden blootgesteld. Dat moeten we niet willen.
1953. A northwestern storm drives the water of the North Sea up to a record level. Many dikes are too low or are unable to withstand the pressure of the sea. Large parts of Zeeland, South Holland and North Brabant are flooded. 72,000 people are evacuated. 1,836 are killed. The 1953 catastrophe made a deep impression. 2 weeks after the flood, the government formed the Delta Commission to make sure that a disaster like that could never happen again. On the recommendation of this committee, the Delta works were constructed in the following decades, considerably reducing the chances of another inundation.
De stormvloedkering in de Oosterschelde is gesloten. De deltawerken zijn voltooid.
But have they? Or will they soon fail to meet the requirements of our time?
Good morning. My name is Jaap van Dijk. I'm Scientific Director of Deltaris and leader of the Dutch Delta program team. And Deltaris is the Dutch research institute that addresses the so-called Delta issues. We are founded by the Dutch government, and our mission is to answer the question that closed the video. The Netherlands is located in a delta where the rivers Rhine and Meuse flow into the North Sea. And as a consequence, a large part of the Netherlands is flood prone. 2/3 of our population lives in these areas. And there we earn most of our money. And to answer the question, will our flood protection system fail? Yes, it will, if we do nothing. Because of the combination of sea level rise and soil subsidence, the Netherlands is sinking, sea level is going up, increased river runoff and population growth, flood risk will increase in some areas by 4 to 8% annually. If we do nothing, this means that the expected flood damage at the end of this century will have increased by a factor 30 to 700. So we have to act. But how? How much, when and where should we act? Now these are the questions that are answered by our modeling analysis. Our work provides objective flood protection standards by weighing investment costs on the one hand and the losses in case of a flood on the other hand. Before our study was done, the policy options towards update of the protection standards ranged anywhere between no change and an increase of the standards everywhere tenfold. Do nothing would mean no investment, but a much higher flood hazard. Increase the standards everywhere tenfold, as proposed by the Second Delta Committee, would need an investment of 11.5 billion euro. Our methodology has provided objective flood protection standards and put an end to the contentious political discussions on how much to improve the Netherlands flood protection. So our model helps the Dutch government to spend its budget wisely. In 2012, the Ministry of Infrastructure and Environment decided to change of policy according to our advice, namely to only increase the standards in 3 specific regions as compared to the prior advice to increase the standards everywhere. In this way, 7.8 billion euro on investment costs that had already been included in the national budget will be avoided. And at the same time, our proposal reduces the total expected damage costs due to floods in the Netherlands by 2/3 compared to a no-change policy. Now, our project is part of the Dutch Delta program that aims to protect the Netherlands against flooding over the next 100 years. And the Delta Commissioner, Wim Kuijken, is appointed by the Prime Minister to lead this multi-billion-dollar project. And he has recorded a message for us. Let's listen what he has to say.
Good evening, honourable members of the jury, ladies and gentlemen. I would like to express our gratitude for selecting our team as one of the finalists for the prestigious Franz Edelman Award 2013. On the highest political level, we are now discussing the standards to protect the Netherlands against flooding. And that's the reason why I regrettably cannot be with you today in person. I'm convinced that my colleagues will do an excellent job explaining to you how this project provides essential information for this important decision-making process. I hope you enjoy the presentation.
In the Netherlands, the level of flood protection is determined by the Water Act. And this act formulates flood protection standards for all the 53 large dike ring areas, or polders, as you wish. The dikes surrounding these areas have a total length of 3,500 kilometers, more than 2,000 miles. The standards are defined as admissible flood probabilities per year. They range from a probability on average 1 in 1,250 years for the areas along the upper parts of the Rhine and the Meuse rivers, these are the green areas in the picture, to 1 in 10,000 years for the most important areas along the coast, these are the red areas in the picture. These standards, in effect today, are still the same as those defined after the 1953 flood. Many of the existing standards were partly based on Van Danzig's pioneering Econometrica article on determination of optimal dike heights, which is considered as the start of operations research in the Netherlands. And we see our contribution as a continuation of that proud history. But some parts of the standards were never substantiated by scientific analysis. Nevertheless, even today, the existing flood protection standards in the Netherlands are the highest in the world, compared, for example, to here, the standard in the USA of 1 to 100 years. In 1993 and 1995, high flows of the Rhine and the Meuse rivers led to very risky situations. In 1995, the Netherlands had to evacuate more than 250,000 people because of fear the levees would break. Now, this event was a wake-up call to the nation. Moreover, since 1953, the population of the Netherlands had almost doubled and its GDP had increased fivefold. And all these developments and the awareness of the increased sea level rise and climate change strengthened the consensus that the standard had become outdated. Therefore, in 2006, the Vice Minister of Water Management, Melanie Schultz, who is currently the Minister, asked Deltaris to perform a cost-benefit analysis to flood protection. And this was the birth of our project. At the top of our project organization is the Delta program, led by the Delta Commissioner. And at Deltaris, we decided to put together the best team possible with experts from research institutes, from government, universities and consultancy firms. These are the CPB, the Netherlands Bureau for Economic Policy Analysis, the consultant HKV, Tilburg University and Delft University of Technology. Our project started in 2006 and we delivered our final report in 2011. And the final recommendation was unexpected by both experts and the policymakers, as it was in substantial conflict with the prior advice and existing policies. In 2008, the renowned Second Delta Committee, chaired by the former Minister Kees Veerman, advised the government to increase the standards of all dike rings areas tenfold. This would mean, for example, that a standard of 1 in 2,000 years would become 1 in 20,000 years. Achieving this level of protection would require an investment of €11.5 billion. Following on this recommendation, the government increased the flood protection budget by €1 billion yearly from 2020 onwards. But in 2011, through Operation Research Analysis, we were able to convince both the chairman of the Second Delta Committee and the government that this was not needed. An increase in protection would be needed in only 3 areas where flood risk is the highest. And as a consequence of our advice, the government has then decreased the corresponding budget. This remarkable result has been obtained by using innovative operations research. While our model was developed for the Dutch situation today, it's actually quite flexible, and I'm convinced that our model can also provide great benefit for other countries where flooding is a continuing risk. For instance, last month I was in New York together with our Minister Melanie Schultz, and we met officials from New Jersey, from the City of New York, and Mr. Donovan, the Federal Secretary of Housing and Urban Development. And we talked about the recovery after Hurricane Sandy, which will cost more than $60 billion. Now next we will have a look in other parts of the world which recently faced flooding. And after this video, Karel Eigenraam will tell you more about our model. And Karel is economist from the Netherlands Bureau of Economic Policy Analysis. And he is the one who extended and improved the original work of Van Dantzig on optimal dike heights. And in the scientific water world of the Netherlands, he is considered Van Dantzig's successor.
August 2005. A hurricane lands in the US state of Louisiana, hitting the city of New Orleans. Dikes break and the city is completely flooded. The affected area is disrupted for months and a large part even for years. More than 1,800 people are killed. The damage runs to some $27 billion.
The aim of our project is to propose new values for the national flood protection standards based on an optimizing cost-benefit analysis. The image projected here shows the optimization problem in its most simple static form. Clearly, higher dikes mean higher construction and maintenance costs. However, the higher the dikes, the lower the expected flood damage costs. Absolute protection against flooding is impossible. Regardless how high the dikes may be, there will always remain the potential for flooding. Our approach is to minimize the long-run sum of the investment cost and the expected flood damage costs. Thus formulated, we have an economic question with a rational solution. However, in the end, a political decision has to be taken because in our calculations many value judgments are made, for instance on the value of human life and the extent of risk aversion. Moreover, there is the equity issue. However, not only the how much, but also the when to invest question is important because of dynamic effects. The probability of flooding is rising due to climate change and soil subsidence. and both population and wealth are increasing, hence the damage by flooding increases. In combination, expected damage is increasing, that is, the probability times the magnitude of the damage by flooding. We spent several years and millions of euros to collect huge sets of data to construct and estimate the following important model elements for each of the segments of the dike rings. A cost function for subsequent dike upgrades, a formula for the flood probabilities as a function of dike height, now and in the future, and a formula for the damage costs, now and in the future. In the paper submitted to the judges, we illustrated the detail in which the information has been gathered using the example of investment costs. We showed the extent of knowledge used by the example of the flood probability along the coast. Of course, we are aware of the difficulty of determining the small flood probabilities used in the Netherlands. Flood probabilities are the combination of many factors relating to the loads on the dike and to the strengths of the dike. The best approximation of the flood probability based on the results of all detailed studies is the specification shown on the image. The flood probability depends exponentially on the relative height of the dike. The estimates of the parameters are the combined results of sophisticated statistical analysis, physical models for the strengths of a dike, historical data about past events going as far back as the year 800, and nowadays many thousand simulations of many types of very bad weather conditions. For more detailed explanations, I refer you to the extensive technical literature on these subjects, which we had to master for our project and which is detailed in our paper. Now I'd like to explain a bit more about how we estimated damage costs. To get a good idea of the extent and impact of a flooding incident, the 35 water boards and provinces constructed more than 700 flood simulations using regional hydraulic models. In a moment, we will show one of the larger of these flood simulations. The animation starts at the moment a breach occurs in dike ring 43, a dike ring with a population of 300,000 people. In this animation, the breach is located at the east side, which is far away from the sea, so the whole dike ring 43 is flooded. The flood stops only temporarily when it hits a secondary dike. It seems to halt when reaching the primary dike that separates dike ring 43 from dike ring 16. However, in this simulation, the flood is so big that it overtops even this primary dike, so that dike ring 16 is flooded as well. As you can see, the water will reach a depth of around 4 meters in the western part of dike ring 43, which means that the material loss in that area is high and almost complete. The total damage in these two dike rings will be 75 billion euro. For each of these 700 flood simulations, we combined local information about speed of the water, inundation time, and water depth, together with detailed geographical information systems featuring data on number of persons and households, on real estate objects, infrastructure, and so on, multiplying the damage costs in each flood simulation with the probability of that flood occurring, and then summing over all flood simulations gives an average value for the expected damage in each of the 53 dike ring areas. My colleague, Dick den Hertog, professor in operations research at Tilburg University, explains how we approach the optimization question mathematically.
The optimization problem is to minimize the total long-run costs, consisting of expected damage costs and investment costs for upgrading dikes. Most of the dike rings contain multiple dike segments. This is a picture of the Bommelerwaard. The dike ring consists of 3 segments, since it is surrounded by 3 different rivers with different characteristics and thus different parameter values. Segment 1 is the northern dike along the river Rhine. Segment 2 is the southern dike along the river Meuse. And segment 3 is the western dike along the river that connects those 2 rivers. I live here with my family. In 1995, we were also evacuated. Fortunately, nobody was hurt, even though the water reached all the way to the very crest of the dike. Dynamic programming can be used for dike ring areas up to 3 segments. But in the case of more segments, the state space is too big. We also tried an impulse control approach, but it appeared that this method cannot efficiently solve problems with multiple segments. We therefore developed a mixed integer nonlinear programming model. We don't have time to discuss this model in detail. We only illustrate the structure. We discretized the time, and the binary variables are the decisions whether a dike is upgraded at a certain time or not. Note that we need a binary variable because of the fixed investment costs for upgrading a dike. The continuous variables are the amounts of heightening of each segment of the dike. Both the expected damage and investment costs are non-linear functions. The investment cost is a function of the cumulative dike heights, since heightening a dike also means broadening the dike. So upgrading high dike is more expensive than upgrading a low dike. This investment cost function leads to a non-convex objective function. However, we have much evidence, both from theoretical and numerical convexity analysis, that the resulting optimization problem is convex in a wide neighborhood of the optimal solution. Note that we also discount the investment and damage costs. The biggest problem has 10 segments at a time horizon of 300 years, with a discretization period of 5 years. A time horizon of 300 years is necessary to get a stable solution for the period until 2050, which is the relevant period for policy. The corresponding optimization problem has 610 binary variables, almost 1900 continuous variables, and in total more than 3,000 constraints. We used the outer approximation method that is implemented in AIMS, which uses Cplex and Conopt as solvers for the linear and nonlinear problems. Due to recent developments in mixed integer nonlinear programming, we could solve problems up to 6 segments. Using additional heuristics developed by our team, we were able to also solve the largest problem with 10 segments within 1 hour. Solving all 53 dike ring areas took about 1 day. For more details on the model and solution methods, we refer to our paper in operations research. The model and solver were implemented in a user-friendly software package. Let's have a look at the optimal solution for a dike with 3 segments. In this figure, we have the years on the horizontal axis and the flood probability on the vertical axis. The flood probabilities of all 3 segments are the 3 sawtooth curves in green, yellow, and red. The first upgrade is in 2034. Note that all segments are upgraded at the same time. This is plausible since upgrading a segment when another segment is still the weakest does not improve the safety very much. Of course, the amounts of heightening for the three segments may differ. Immediately after an upgrade, the probability decreases sharply. Thereafter, it increases again due to rise in the water level. And then, in 2075, all the three dike segments are upgraded again, and so on. Finally, we defined the economically efficient standard as a central value for the probabilities associated with the optimal investment strategy. This is the blue curve in the picture. Choosing the value of the efficient standard in 2050 as the legal standard yields a stable flood protection policy for decades ahead. Hence, the efficient standard becomes 1 in 4,000 years. Note that the current standard is 1 in 2,000 years. So regarding the dikering area in this picture, we advised improving the legal standard from the current probability of on average 1 in 2,000 years to 1 in 4,000 years. We also performed an extensive robustness analysis for the efficient standards. The relative positions of the protection standards appeared to be robust. My colleague Jaro Kind, senior economist at Deltares and project leader, will now discuss the results and impact of our project.
The most important results of our project are the efficient flood protection standards. Here you see the efficient standards according to our model on the left map and the existing standards on the right map. The existing standards are highest in the central western part, the red color, and lowest along the rivers, the green. The other areas, yellow and orange, are in between. If we compare the two maps, we observe the following. 1. Flood protection in the northern part is more than sufficient. Existing standards exceed efficient standards. 2. Flood protection for the most valuable part of the country, the central and western part, is still appropriate. The existing standard equals the efficient standard. 3. The existing standards along the rivers are much lower than the efficient standards. Flood protection should be increased. So if we compare the standards in more detail, we conclude that flood protection should be improved in the areas near Rotterdam, for the fast-growing city of Almere, and for most areas along the Rhine and Meuse rivers. For the other parts of the Netherlands, the existing flood protection is more than sufficient. So how can we best explain those remarkable differences between the existing and efficient standards? This picture illustrates the perception of flood risk when today's legal standards were determined. High risk for coastal areas below sea level and low risk in river areas above sea level. The picture on the left shows the maximum water depth obtained from the new flood simulations. Hence, high standards for river areas and low standards for coastal areas are the logical outcome. Let us look at the total investment cost and damage cost of the different proposals for new standards over the period until 2050. This is the period for which the new standards will apply. For no change policy, no additional investments are required. The expected flood damages will amount to 15 billion euro, and these are also the total cost. For the advice of the second Delta Committee, an investment of 11.5 billion euro is required. Compared to the no change alternative, the damage cost will decrease with 90% to 1.5 billion euro. Hence, the total costs are 13 billion euro. If our advice would be followed, the investment costs are 3.7 billion euro, and the expected damage cost would be 5 billion euro. The total costs are 8.7 billion euro. So clearly our advice leads to the lowest total cost and hence is the most efficient. We get 2/3 of the benefits of the advice of the second Delta Committee for 1/3 of the costs. Note that the damage cost also includes the cost of human life and other aspects which are difficult to value in monetary terms. We therefore extensively performed sensitivity analysis. Those show that our conclusions are robust. The political decision on the update of the protection standards is taken with great care. It's a costly decision and involves a trade-off between efficiency and equity. Our report was discussed in the Water Advisory Committee, chaired by Crown Prince Willem-Alexander, who will become our king in a few weeks. And one of our team members, Karel Eigenraam, personally explained him our model. And this committee stated, the studies provide solid building blocks for the further discussion on an updated and robust flood risk management policy. The chairman of the second Delta Committee wrote, I agree with the decisions of the ministry to follow these recommendations, and this differs a lot from his own earlier advice. In 2012, during the former government, the House of Parliament agreed with our conclusions in an anonymous motion. And finally, the Ministry of Infrastructure and the Environment decided that a general tenfold increase in protection standards is not needed, and that only in 3 regions an increase in the protection standards is necessary. Let us now listen to the Delta Commissioner, who has recorded some conclusions on the impact of our project.
In the Dutch Delta approach, cost-benefit analysis is also embraced as an instrument to achieve efficiency in flood risk management. This is innovative. The necessary knowledge and tools for adequate flood risk assessments have only recently become available. The Netherlands leads the way by the use of the risk-based approach to flood management. The cost-benefit analysis in which operations research techniques were used shows that for the decades ahead, it is not necessary to increase the flood protection standards tenfold for the entire country, as recommended by the second Delta Committee. This project also showed that higher protection levels are needed only in 3 specific regions. The coming year, I will present a broadly supported set of Delta decisions on flood risk management, freshwater supply and spatial adaptation to the government. My proposal for new flood protection standards will closely follow the main conclusions of this project, which have been recognized already in discussions with the water boards and the provinces. Operations research techniques have provided policymakers with an objective basis for decision making. Therefore, this innovative project has contributed significantly to improved flood protection in the Dutch Delta, while at the same time steering public funds in the most efficient way. Thank you very much.
At a global level, expected flood damage is intensifying due to population growth, economic development, and climate change. And in many countries with significant flood risk, legal standards do not exist or are not based on economic principles. In such countries, our methods can support the often difficult task of setting proper legal standards for flood protection and allocating the necessary financial resources. It can prevent unnecessary human loss and save billions of euros in flood damage. The omission of cost-benefit analysis in flood risk management may turn out to be penny-wise but pound-foolish. The optimization model and solvers are implemented in a user-friendly software package to enhance portability. Authorities in France, China, Pakistan, and the US have contacted us to discuss the methodology. Our project was innovative in flood risk management and operations research. The project was complex, involving more than 5 different disciplines. It ran from 2006 until 2011, 6 years in total. And the budget for research and data collection was over 4 million euros. Dozens of persons were directly or indirectly involved, from different organizations like ministries, provinces, all water boards, several universities, research institutes, consultancy firms, etc. And thanks to the time and budget we had, we were able to get into the details of a wide variety of flood risk situations. And this distinguishes our advice from the second Delta Committee, which was based on a more global analysis in a relatively short time span. So the quality of our project is widely recognized. Since 2006, our project and recommendation survived already 4 different governments. And these governments had coalitions from very different political parties. And in each government, a member of the cabinet took explicitly responsibility for our project and for the results. So at this time, the government minister who is responsible for our project is Minister Melanie Schultz. She is the highest in rank at the Dutch Ministry of Water, of Infrastructure and the Environment, and member of the cabinet. And so we are extremely proud that she has recorded a special video for the jury and public of the Frans Edelman Award. With her words, we finish our presentation.
Dear judges for the Frans Edelman Award, I wish to congratulate the Dutch team for being a finalist of your prestigious award. 7 years ago, while I served as Vice Minister for Water Management, I asked for a cost-benefit analysis as an objective basis for new legal flood protection standards. The outcome shows startling differences from the earlier advice to increase the standards tenfold everywhere, and it led to significant, verifiable cost avoidance. The Ministry accepted the results in 2012 and indicated 3 target areas where the standards may be increased. In this cost-benefit analysis, the team used sophisticated optimization techniques, and the results of their analysis will play an important role in the final political decision on new protection standards for the Netherlands. These new standards are an important part of my agenda as government minister, and I plan to send them to Parliament next year. I'm certain that the new standards improve flood protection in the Netherlands, and I'm convinced that this study will be referred to by many people in the future, just as it is still the case with the findings of the first Delta Committee published more than 50 years ago. And I'm also confident that the new cost-benefit analysis will form the basis of our updated flood protection policy. It will help secure both human lives and our economic interests in the decades to come.
Thank you very much for your presentation.